Hello, my name is Dr. Reza Said Kandezi. Today, we are going to talk about the internal JTAG. Uh, the discussion is about the instrumentation standard for the embedded instruments, or as we call it, IJTAG, and we are going to use IEEE 1687 as our framework. We are going to talk about the why this standard exists, and we are going to talk about the limitation of the legacy standard for this purpose, which is the IEEE 1149 Part 1, and then talk about the motivation that we had to develop the IEEE 1687, and talk about the definitions, the protocols, and how we could actually run such a system on the system on chip designs. Now, as the integrated circuits basically become more advanced, we saw that the fundamental transformation in how test or debug or monitor the functions that are implemented become a little bit difficult. So traditionally, many of these operations, like testing logic and like tuning the system, was conducted by external tools. But right now, with the current technology, we don't have that access and that ability. So we need to kind of like see another solution. We are seeing a broad industry shift toward the embedding these functions directly inside the silicon itself. So basically, these are what we call embedded instruments. Now, what exactly, let's talk about that, are these embedded instruments yeah. So those instruments basically can include like a internal scan chain or built-in self-test blocks, or even like PLLs considered as those embedded instruments, the temperature monitors, security wallets, or the performance monitors. All of these are now basically embedded on the chip, and as you know, they are all playing a very important role during the manufacturing test or field diagnostics, and even real-time optimization during the operation of those devices. So let's, before going forward, let's answer the very fundamental question: why we embed those instruments? Okay, so the answer is the complexity. When the silicon on chips devices evolves into a multi-core or a multi-domain system, okay, and we had like advanced analog, digital, or RF component, it's not kind of like possible to rely on external probes or test pins, basically. Okay, so we need a way to observe and control or configure, and it has to be happen inside the chips. Now, as we said, traditional access methods, like even those defined in IEEE 1149 Part 1, which is called boundary scan, which is also known as boundary scan, were revolutionary, basically create a revolution in these matters, okay? And they allowed a control and observe in a clean and a standard way. But the problem was that those methods, they never designed to deal with the hundreds of embedded instruments, okay? And when we have multiple IP cores, okay? So basically it leads to the problem like excessive scan times, or like power waste from unnecessary shifting, or rigid architecture that can't basically adapt to the changing requirements, and also had a severe integration challenge, basically in the situation that we deal with the third-party IP block. So now what we should do to address this problem? Now we need an intelligent, a scalable kind of like mechanism, okay? The one that's actually modular, and we can reconfigure that, okay? It's vendor neutral and automation kind of like friendly. Basically, this is exactly what led us to develop IEEE 1687, or as we call it, IJTAG. Okay. Now, before we move forward, let's go deeper on the boundary scan and the limitation of 1149 Part 1. Now, this standard, the boundary scan standard, provide, although it is provide an elegant mechanism, okay, to basically control or observe the pin level, okay, using the scan cells or the scan chain, and also give us ability of the board level testing, okay, in a situation that physical access is not easy to achieve, okay. The IEEE 1149 Part 1 originally developed to help to test the connection between the chips, okay, or on a circuit board, okay. But when the electronic component becomes smaller and more integrated, okay, it becomes impossible to touch their pins with test probes. So that's why 1149 basically solved that problem and kicks in and solve that problem. Now, however, with all that benefits that this standard, the IEEE 1149 Part 1 brings to the table, it has a significant shortcoming. And it's kind of like show itself when we're dealing with the internal instrumentation. So it worked well for the testing pin connection, but it wasn't designed for accessing or managing complex logic inside the chip. Okay, so basically the standard was built for the external interface testing, not for internal instrumentation or instrument like thermal sensor or like BISD modules, which require a deeper and more flexible access methods. Now, assume a flat chain structure. Let's talk about a clear the concept of the limitations. If we assume a flat chain structure, okay, the IEEE 1149 Part 1 basically expects that all the test elements are connected in one long linear chain, and it cannot be changed during the operation. So this flat chain means every instrument or register is linked in a single sequence, like bits or a string. Okay, so you can skip the element or reconfigure the path without physically redesigning the chip. So that's one of the problem that kicks in to create that limitation. Now, another one is that we can't select the scan path dynamically. So once the scan path is set, you can't change it. Okay, so everything must go through a fixed path. So if you only need, like, for example, test one part of the chip, you still have to shift the data through all the other parts, okay, which basically is wasting time and energy. So basically that all, like, the legacy method brought by IEEE 1149 Part 1 lacks the on-the-fly reconfiguration. reconfigurability. Okay, so that standard also has been limited to metadata support for complex internal access protocols. Okay, so it doesn't support ways to describe instruments, what they do, how to control them, or what data they output. And also there is no built-in mechanism to say like this register controls a temperature sensor or this bit starts a self-test. This lack of this metadata basically avoid us to have an automation and vendor independent integration, and it makes that very difficult. These limitations basically created a pressure to define a scalable, ready to reconfigure as needed and automated method that connect and manage internal instruments, or basically what we are gonna talk as IEEE 1687. So as chip got more complex, basically we needed a way to access internal tools, and this access should be efficient, flexible, and vendor neutral. So the goal became to develop a standard that could manage the instrument access like a network. Okay, it's not a single chain, it's a network now in this standard. IEEE 49 Part 1, one of the limitation is that it cannot dynamically change the scan pass. We already mentioned that. So if we have one scan pass, okay, for the instruments and it remains fixed, permanently fixed, we cannot change it during operation. Okay, so another problem to sum up is a scale problem, because modern silicon on chips technology may have hundreds of instruments. Okay, so and all of them are embedded. So each responsible for monitoring, and all of them, each of them is responsible for monitoring or controlling a part of the chip. So basically, these instruments could include things like voltage monitor, memory tester, or signal integrity tools, and accessing each one of those instruments through a fixed scan chain basically is highly inefficient, especially when the number of those instruments grow and grow and grow each day. Okay, so it is basically an efficiency impact, because in old ways, in 1149 Part 1, we had to shift through all the modules in order to test one of them down the road. Okay, so for example, if you wanted to if you have 128 instruments and you only want to access the instrument number 127, you still have to shift the data through all the 126 instruments that are before our targeted instrument in the scan chain developed based on the 1149 Part 1. Now, the IEEE 1149 Part 1 basically cannot support accessing and controlling sophisticated embedded logic and their analyzers, which require a very complex configuration sequence. Okay, so basically these logic analyzers that are embedded in the chip need multiple steps and parameters to set up. But IEEE 1149 Part 1 only allows a simple data shift and can't manage such a complex sequence. Okay, so another fact is that the running complex built-in self-test sequences, BIST sequences, basically require context-aware configuration. and should have a multiple instruction phases, which is not supported by 1149 part 1. Okay, now that BIST is like a self-checkup feature inside the chip, and when we want to use it, we must first set the parameters like test patterns, timing, and then start the test and finally read the results. Okay, but in 1149 part 1, the standard lacks the ability to handle this step-by-step sequence. Okay, because it only knows how to shift bits in and out with no memory of the prior actions. Okay, and another fact is that the monitor, the dynamic monitoring, which basically modern technology need something like dynamically monitoring thermal sensors or streaming performance. Okay, and that's require a parameter passing and sequence execution capability. So all of today's chip normally need to continuously be monitored. Okay, and that monitoring, as we said, involve passing live parameters, and it has to be repeatedly executing procedures, which IEEE 1149 part 1 can't do that. These monitoring instruments like thermal sensors should be pulled basically regularly to check the chip temperature during operation. Okay, so this requires a loop-like behavior. Okay, when the chip is asked to read sensor, apply the threshold, or adjust the behavior, and it's happened repeatedly. Okay, now IEEE 1149.1 only supports the shifting data in and out. So it has no native capability for procedural invocation or instrument kind of like orchestration in our contemporary chip designs. Now, that standard, IEEE 1149 part 1 does not provide basically a common method to describe the scan connection when we have multiple pre-designed components that we call it IP. Okay, the IP blocks, and they are combined into a very like a large chip. Okay, so these modern silicon on chips SoC designs, in those design, we normally use the pre-made building blocks from like different vendors. Okay, that's called the intellectual property blocks, which the short of it is that IP blocks. And we do that because we wanted to like save time and cost. But IEEE 1149.1, the part 1, assumes everything is connected in one long chain. So it doesn't support like a hierarchy in the design, okay, where each block might have its own scan system. Okay, so result basically in the complex and error-prone integration, okay, that had a hardcore RTL for scan access was also is become important. So accessing those instruments, okay, with the old standard, the IEEE 1149.1 often requires like a writing scan connection directly into the hardware code. Okay, so which is complex and basically increase the chance of mistakes. That RTL, which is basically to know it, is register transfer level. RTL is short for register transfer level, is a low-level language basically used to design chips. Okay, so engineers should manually write connection logic to include every instrument in the scan chain, and this process is tedious. Okay, especially when we integrating a third-party IP. Now, that 1149 part 1 basically forces the scan structure to be fixed. Okay, so we can easily reuse or reconfigure it for different cheap projects or kind of like versions. Okay, there is no automation in a scan control for the embedded modules. Okay, for the embedded modules. In 1149 part 1, there is an automation, but it's only for the testing the external kind of like ports. Okay, so the pin input output pins. Okay, so when we're talking about the embedded modules inside the logic of the chip, we don't have an automated kind of automatically generating a scan control. So and in another kind of like aspect, which is the inflexible design of those that standard is that we want to build a chip like Lego. Okay, so it's easily plug in blocks from different sources. Okay, and but IEEE 1149 part 1 doesn't allow that, doesn't support that. So that's basically create the vision and the motivation for developing the IEEE 1687, which basically providing the access, not just the scan. It's providing the access. Now, the IEEE 1687 allows you to access a specific instrument inside the chip without needing to go through all the others, okay, in a fixed sequence. So basically, instead of scanning through every embedded tool to just reach the one that you care about, okay, this standard lets you to directly open a path to that one instrument, okay. The scan path through this standard to the IEEE 1687, the IJTAG, can be dynamically reconfigured. So only the necessary parts on the chip are activated during each test. Okay, so it's basically introduced what we call it a reconfigurable scan network, RSN, okay, which is made of smart switches and let us navigate different passes for the chip as based on our need. Okay, so like a GPS system choosing the fastest route instead of always taking the same road. Okay, so this is kind of like the situation. Now, basically in this instrument, in this standard, only the instrument you want to use is turned on, okay, or made active during the scan. The other remain off or bypassed. Okay, this basically selective activation give us a better performance, make the power consumption get decreased and avoids interference. Okay, so it helps to keep sensitive or security-related instrument isolated unless we want to intentionally access them. Now, there is another aspect to this standard, and it's the standard interface that promote portability. Okay, what that means? This IEEE 1687 basically uses a standard way to describe how to connect and control the instruments. Okay, so IP blocks and test procedure can be reused easily across different tools and design. This means like a temperature sensor block from a vendor A can be reused in a new chip design or tested with tools from vendor B. Okay, because everyone speaks at the same language. This reduces time and effort in integration and promotes the IP reuse, basically. Now, this test system can change its behavior based on what's being tested. It could mean adopting passes, sequences, and commands in real time. So, for example, the chip might skip certain instruments during the manufacturing, but access them frequently during field diagnosis. Okay, so IEEE 1687 lets the test basically infrastructure adopt dynamically and match the use case, like switching tools depending on the job. Now, the top level goals of the IEEE standard 1687 are are the copies that you see on this slide. This IEEE 1687 allows us to activate only the parts of the scan pass that we need. Okay, and we are gonna do that using the segments that can be turned on or off based on the test requirement that we have. We are gonna talk about those segments later on in an upcoming slide. Now, you can imagine a chip with 100 instruments, but you only need to access like 3 of them. Okay, basically IEEE 1687. Using that, you can insert segment insertion bits or SIBs, segment insertion bits. It's like switches that open only the needed sections. Okay, so it skip the rest of the sections. So this heavily reduces the time and power and the effort involved in the testing. Now, beside that, this standard supports organizing the instrument into a modular blocks. Okay, so designer can reuse them in different chip without worrying about how they're connected. Okay, so this is another aspect of that. Benefits and the goals of IEEE 1687. Now, another fact is that instead of manually wiring the scan pass in hardware code, okay, like RTL, this standard lets you to like describe how instruments are connected using a high-level description language that we call it instrument connectivity language, ICL. Again, we are going to discuss that in upcoming slide. Basically, traditionally, we had to write the complex RTL code to specify how each test register is connected. Now, with this standard that introduces ICL, which is a human readable way to declare the connections, okay, it helps automate tool integration and basically eliminate all the manual scan wiring. So that's very kind of like significant characteristics of this standard. Now, IEEE 1687 also introduces a specific language, okay, that we call it procedural description language, PDL, and we use that to write test steps in a readable kind of like procedures and make them easy to automate, to get automated. Okay, so and easy to share and reuse across like different tools or vendors. Okay, so the flexibility of these standards is very significant. Now, let's talk about what that IEEE 1687 introduces to our technology. Okay, we have a reconfigurable scan network, or we call it RSL, which enables dynamic path selection, and it uses the segment insertion bits for that to open or close a certain scan pass. Okay, so basically allowing for conditional access to the instrument. Okay, so the RSN is like a smart modular scan highway, okay, that make us able to open or close routes using tiny switches, which is like that ISB, the segment insertion bits. Okay, and basically by using those, we reach only the instruments that we need. So this IEEE 1687 basically introduces that RSN, and using that, basically you are building a tree-like or like a branchable network of instruments. So each branch has a SIB, like a small 1-bit controller, okay, that decides whether that segment is included or we have to skip that during the scan. And that way, it significantly reduces the time and energy that we need for the test or monitor. Now, another definition that this standard introduces to the field is instrument connectivity language, or ICL, which basically declares the interconnection of the instruments and SIBs in a human readable and format, which supporting all the IP abstraction and hierarchy that exist. Okay, so ICL basically is a special text-based language. Okay, and it describes how the instrument and scan segments are basically connected to each other inside the chip. So the design tool can understand and automate the access. So basically, instead of the hard coding the every connection in RTL, we use ICL to describe the structure of the scan network, which basically means which instrument exists, how they are connected, and how to reach each one of them. And it is readable by both humans and software tools. So that's very important. Another factor is procedural description language, or PDL, which describes how to operate an instrument. So basically that PDL is a script-like kind of like language that tells the system what to do with an instrument. So it could be run a test or set a mode, something like that, and it happened without needing to manually shift every bit. Okay, with that clock shift register that we have in JTAG in IEEE 1149 part 1 here, without need that shift register to happen. So the PDL basically makes this procedure possible by basically providing a way to write that procedure or sequence that describe the test steps. So we are basically developing the scenario of the test using the PDL. Okay. There is another definition, the instrument port model, or IPM, which basically specifies the input-output ports of an embedded instrument and basically defines what the instrument's output and inputs are and what they mean. So the tools know how to interact with the instrument. Okay, so it's like a USB device interface. Okay, like when it's connected to the keyboard or storage. That embedded instrument need a clear definition of its connection point, okay, and the behavior. So IPM describe that and basically make sure that when a test tool accesses an instrument, it knows exactly how to communicate, okay, regardless of who designed the chip, and basically promotes interoperability and reliability in the system. Now, let's go over the IJTAG feature and review them. Okay, so what are the features of this standard? First feature is reconfigurable scan paths, which is means dynamically open or close branches to access the only instrument that we need, or the only node that we need. Okay, so instead of shifting through a fixed scan chain, we let the scenario to dynamically turn on or off the branches in the scan path, so you reach only the instrument that you need. So another aspect is segment insertion bead, which is a 1-bit control element for enabling and disabling the scan segment. It's a simple 1-bit control and decides whether a certain part, or as we call a segment, of the scan network should be active or bypassed. Okay, so think about it as a gate or switch on a road. Okay, it either let you into that into a side street, okay, or keep the gate closed. So you stay on the main road, or you can enter the side street. Okay, so that 1-bit element is lightweight and efficient, but it enables powerful runtime path control inside the chip. Now, another aspect was the instrument connectivity language, ICL, which is a language for scan topology and path declaration, which basically is a description language that defines how instrument and scan segment are physically and logically connected to each other. The next one is PDL, procedural description language, which is a description language that defines how to operate each instrument. Okay. Next one is IPM, the instrument port model. As we said, it defines the input-output of an embedded instrument and what each one means or does, so the tool can interact with those consistently. And there are tool automation support feature for this IJTAG kind of like architecture, and it's because IJTAG is built with a clear structure and standard language. Okay, so it can be fully supported by automation tools for everything from designing to debugging. Okay, so in the real world, these tools are used basically for designing trees, simulation, test pattern generation, or failure analysis. And since IEEE 1687 basically provides a structured machine-readable format, so all these stages can be automated. Okay. Now, let's dive deeper into the RSN, reconfigurable scan network. This RSN is what allows the flexible, efficient access to the instrument, the embedded instrument in the chips. Okay, so these has some also key characteristics. One is that it is modular, meaning the components can be added or removed without redesigning the entire scan chain. It is scalable, meaning it efficiently handles the large number of the instruments. So the RSN is designed basically to work efficiently even when there are hundreds of thousands of hundreds or thousands of instruments on the chip. So as the chip grows more complex, basically the number of the embedded instrument increases, Two, so the RSN avoids the inefficiency of the scanning through everything by only activating the necessary scan pass. It's navigable, so that means the pass can be dynamically selected at runtime at any moment during the operation or testing. Basically, we can use the SIBs, the segment insertion beads, to change which scan pass you are using and basically choose exactly where to go inside the chip. Okay, so another factor is that is efficient. So it reduces scan time by accessing only relevant segments. So this is kind of like the characteristics of this topic, the RSN, the reconfigurable scan network. Now, we also mentioned the segment insertion bit several times. Let's go a little bit deeper on that. So is this SIB is, as we said, is a 1-bit register that basically controls and access to the scan segment. So it's like a relay. Okay, it either lets you to access or it gives you no access. So it enables the access to the states. Like for example, when the bit is 1, and it disables when the bit is 0. Okay, so basically that tiny memory cell, 1-bit tiny memory cell that acts like a gate, basically decide whether the scan signal should enter a certain branch or should skip it. Now we have the instrument access ports, which is basically is a named point in the RSN that connects to an embedded instrument, okay, like a scan register or trigger port or configuration register. So it's like a gateway or terminal in the RSN that connects directly to a specific control point. Okay, so inside the chip, instrument like temperature sensors, PLLs, all those modules need an interface to interact with the test tool. So that's IAP is that well-defined interface, okay, where the scan pass enters or exits the instrument. Each IAP is assigned serial data endpoint, if you call it TDI or TDO. It's a unique name and it's fully described in the ICL and PDL, so the tools know exactly how to use it. Like a USB port that has known pins for power and data, and IAP uses that like IEEE scan interface signals, the TDI and TDO, and these defines how data enters and exits. Okay. Beside that, IAP are given logical identifiers, so the tools can call them easily. Now, that IAPs let the test tool reach and operate instrument by following the flexible scan path. So it's kind of like it's not like a hard-coded address like older systems. Okay, so they define how to reach each instrument. They abstract the low-level wiring, okay, and simplify tool interaction. The IAPs are named, standardized, and tool readable. So it's basically enable a full automation, and they support different kind of instrument. So there is a lot of flexibility on using the IAP in different technology. Now, how is the network topology when we talk about the IJTAG testing? Now, the RSN can take several forms, basically depend on the chip architecture. So it The linear topologies are similar to traditional scan chain, but with SIB control segment activation. Okay, so this is a one aspect, linear one. That linear topology connects all the instrument in a straight line, like the scan chain in a boundary scan. But with the added advantage that can skip a segment. Okay, so they are connected in series. Before that, in a scan chain, in IEEE 1149 part 1, we didn't have the option to bypass one through the road. Okay, but here we have an SIB that it could skip a segment. Okay, now we could have a tree structure that provide a hierarchy on the branching, and it's it's ideal for grouped IPs or clusters. And basically it's that tree topology let us organize the instrument into branches and sub branches, which is great for chips that include reusable block or IP cores. We could have more complex design, okay, like mesh or grid topology, with localized clusters and peer access. Okay, that mesh or grid topology basically allows the instrument to be connected like a network of like passes or streets. And it's ideal when multiple instruments need to interact with each other directly, especially So instead of a single line or a tree, a mesh provides multiple paths between the nodes. Okay, which basically improve a fault tolerance and access flexibility. Now, we also can have the cascade structure with basically like with a nested RSN. That cascade structure basically includes a subnetworks inside modules, and the SIVs can activate the entire internal RSN that is nested within the bigger scan network. Okay, so think of this as a network within a network. For example, a system on chip may have a communication block that has its own RSN, so that IEEE 1687 allows us to open a segment insertion bit at the top level, then dive into the sub-level nested RSN inside that IP block. So by that we maintain the modularity while allowing a deep controlled access. Now, to begin accessing an instrument, first of all, we need to configure the segment insertion bits to open the correct branches in our network. So this scan pass in IJTAG is like a map of roads, and that SIB basically is like a traffic lights. So it make them go or stop. Okay, so once the correct pass is activated by that SIB, we use PDL to issue the instruction that tells the tool, the testing tool, what action to take, like shifting the data or triggering the operations. Okay, basically you can think of the PDL like a script or a set of instruction for test tools. Okay, so it tells them how to go through the RSN, how to communicate with the instruments, what result they can expect, and basically handles the instrument navigation and interaction in the tool independent and a standard kind of like way. Once the tool has reached the desired instrument through the activated scan pass, now it can basically shift in commands. Okay, so at this point, the tool basically is connected to the target instrument through the RSN and IAP. Okay, And now it can perform a scan operation just like traditional JTAG, only now it's doing it through a custom optimized path, which saves time and energy. So it might send a test pattern or read a temperature or configure a performance monitor or a certain module. Now, there are some internal structure, both from the hardware component and RTL implementation, that we need to discuss that. Like in the hardware level, the SIB basically comprises several key elements. Okay, the SIB in the hardware basically includes a few small specialized digital logic components that they work together to decide whether or not to include a scan segment. Okay, so the idea of turning on or bypassing the segment is just not a conceptual. It's basically implemented using a real logic gate, okay, and registers inside the chip. So the SIB register the SIB register is a 1-bit flip flop, okay, that stores the value either 0 or 1 that indicate whether the segment is control is enabled or bypassed. So that flip flop is a basic memory cell, okay, and when scan data is shifted into this SIB, this flip flop holds the control bit. So 1 segment is enabled, 0 segment is bypassed. This bit is usually loaded during the shift DR phase, okay, the data register phase of the JTAG operation. Now we have a scan multiplexer, which the multiplexer inside the SIB basically decides whether scan data should be sent into the chip child segment or rerouted around it, so it's bypass that. This multiplexer is like a digital switch that chooses between the multiple inputs and uses the control bit from the flip-flop to select between two passes. We also have an update logic. That update logic basically makes sure that the SIB configuration is stable and finalized before the segment is officially included in the scan pass. So during the operation, data is first basically shifted and then latched during an update phase. Okay, so the update logic basically makes sure that the selected scan pass doesn't change halfway through an operation. So, which basically could cause incorrect testing. So this keeps the SIB state stable and synchronized with the rest of the scan system. Now we also have a TDO switching network, which this part of the SIB logic control basically controls how the TDO, the test data output signals, flows back out. So either from the instrument or directly from the bypass pass. Okay, so after the scan data flows into the chip through the TDI, it must exit through the TDO. So depending on whether the SIB includes the segment or not, the TDO output should be basically routed properly. So the switching network makes sure that the output data is correct, whether the segment was scanned or bypassed. Now, on the other hand, we have the RTL implementation, okay, which basically this simple kind of like hardware code, okay, shows how the SIB stores a control bit and then use it to select the scan pass through a conditional output. Okay, so for example, in this code that you see in the slide, the first line captures the incoming bit into the SIB, okay? And it happened on the rising edge of the test clock, okay? The second part defines a wire, that scan enable part, that activates based on the stored SIB bit, okay? And finally, the TDO, the output, is conditionally selected. So if a scan enable is 1, the scan pass goes through the child segment. Otherwise, it bypasses the TDO. So this simple model shows how selective scan routing is implemented in silicon using just a few logic gates. Now, let's talk about an example of a scenario, of how we could design an RSN. Okay. Let's design a scan network for a system on chip, the SoC, that have 4 IP blocks. It could be like IP1 is like CPU core, IP2 is memory controller, IP3 is analog sensor hub, and IP4 is power management unit. Okay, so each block basically contains 3 embedded instruments. It could be temperature monitor, BIST, or performance counters. And what we want is to efficiently access any instrument without scanning through everything else. Okay, so now, step 1. Think of RSN as a map of roads inside the chip. So each road leads to an instrument. So you don't want to drive through every road to get to one you want. So in this case, we'll use a tree topology, as you see on the image below the on the left-hand side of the slides. This tree topology basically is perfect for the modular IP-based design. Okay, so the top level SIB connects to the 4 branches. Okay, 1 for each block. Okay, each IP block has its own local SIB to control access to the 3 instruments within that IP block. So this structure allows us to open just the IP block that we want, okay, and then go deeper and reach the specific instrument inside it, the one that we target. Okay, so let's say the top level SIB has 4 children. Okay, IP1, IP2, like IP1 SIB, IP2 SIB, IP3 SIB, and IP4 SIB. Each IP SIB controls access to the 3 instruments using its own sub-SIP. So there are going to be SIB, like IP1 SIB dash SIB1 for CPU debugging register, for example. Now, in a real chip, this structure is described using the instrument connectivity language, so that ICL. Now, you can see the sample of that ICL in the right side of the slide, that code that we wrote. This tells us that basically tells the design tools that here's how the scan network is structured, and here's how to open passes to each instrument. Okay, so you can see how we select the segment for each IP block, and then we select the instrument within each IP. Now, let's say you wanted to like read the CPU performance inside the IP1. Okay, for the PDL, the PDL tells the tool that set the top level SIB to enable IP1. and then set IP1 SIB to enable the CPU performance monitor, and then send the scan command to read the value. Now, basically, this sequence gives you the target access, minimal scan time, power saving, and modular design that can be reused in different chips and different scenarios. Now, what about the RTL? How we could have the RTL? Let's go through the example of RTL2, like the register transfer level. That RTL is a way of describing how data moves between the registers and logic in a digital circuit. Okay, so think of RTL as the blueprint, okay, used to design the chip's behavior. Okay, now the segment insertion bits, okay, that was a 1-bit controller, 0 and 1, okay, basically controls that if the segment is selected or activated or is bypassed, okay. We have an example of the code for one RTL in the left side of this slide. Let's go line by line to see what happening inside that code and what those means. So the first line is the clock triggered logic. So this line means they run the next block of the code every time the clock signals goes from 0 to 1. Okay, this is the meaning of the first line. Basically, in a scan operation, TCK, that clock is basically synchronizes that does synchronize data shifting in our testing process. Okay, line 2 is the capture phase condition. So it basically says if blah blah blah. That means only do the next step if we are in the capture phase of a scan. So we make a condition. So if we are in a capture phase, go to the next step. Now that capture underline DR is a control signal that tells the chip that I'm getting ready to load new scan data. Okay. The third line, which is the SIB underline REG, this means that take the bit coming in on the scan input, the TDI, and store it in the register called SIB reg. That TDI is the test data input. It's like a scan input wire. That SIB reg holds the 1-bit value that controls the scan pass. So this is the input data that tells us which instrument should be activated. Now, the fourth line basically generates the control signal. So when we say assign scan enable equal to SIB reg, that means set the value of a scan enable to be whatever is in the SIB reg. So if the SIB reg is 1, then the scan enable is going to be 1. So basically, this signal will control which path we follow. It's like deciding whether the door is open or closed. Okay. The fifth line basically is the route, the output based on the path. So this line means if a scan enable is 1, then set the TDO to child TDO. And if the scan enable is 0, then set the TDO to the bypass TDO. So that TDO is the output, the test output, and the child TDO is the output from the selected segment. Bypass TDO is the output from the fast bypass pass. So if SIB is enabled, we go through the instrument. If not, we skip and continue scanning. Now, When we decide which segment is activated, we said that we have to like have a procedural description language that defines what we are doing. This is a scenario of that testing. So it's basically like a script or recipe that tells the chip what to do with an embedded instrument in a clear and readable format. So we use the PDL to turn an instrument on or off, or send a value to a register, or wait until a certain condition is met, or read the data from a register, or describe how a test is run. Okay, now let's start with that example. We wanted to like have a temperature monitoring instrument inside your chip, and you want to enable a temperature monitor, wait until the data is ready, and read the temperature value. Now, you see an example code. Let's again go line by line and see what's gonna happen. Like the first line, okay, defines the name of the procedure. So we define this procedure names as read temperature monitor. Okay, the second line, okay, the second line, which is the I write, okay, it's considered that the next line is I write. So that double slash doesn't, is not a line. Okay, so the I write line is basically tells us to write 1 to the control register. So it's turn on the temperature monitor. Okay, and the next one, which is the wait until, okay, is a wait signal that tells the test procedure to wait until the monitor says data is ready. After that, we go to the step 3, which is the iRead command, and it's basically read a value into a variable. So it's grab the temperature and store it in a temp result pointer. Okay, and in step 4, which is a print, so it's output to log or console. So show me the result basically, and you can see how easy the code is. It's easily understandable. The machine can read it. The human that works with that can easily understand what's happening. Okay, so this basically what actually happened in the chip is the control register is part of the instrument. The PDL triggers a scan write operation. The status register is continuously scanned until the ready flag is equal to 1. Then a scan read is done on the temperature value, and then the result is stored in a variable that we define. Now we can read that value. Okay, a real PDL file should include a procedure, a variable, loops and conditions, the instrument reference, and comments for documentation. So tools read these files and automatically perform the correct scan operation using the RSN that are defined. So this is our today's discussion. Thank you for joining us. If you have any question, please let me know.